Okay. Good afternoon, everyone. My name is Cathlyn, and I just finished my first year of engineering science. So this summer, I worked under the supervision of Professor Beck alongside Kaya and Litong. So today, I'll be talking about my project, which is to explore the use of single resource model for parallel machine job scheduling with constraint programming. So I realize this is a really long, complicated title, and you may still have no idea what this is about. So why don't we start with the basics, like what is this scheduling and why does it matter? So I'm sure you're already familiar with personal scheduling, whether it's for work, for school, or just for your daily life. So the scheduling I'm talking about today is a critical but complex decision-making process mostly used in manufacturing and service industries. So for example, in a factory, deciding when to use which machine for what, or planning a route for delivering vehicles. But all those types of scheduling have the same goal, which is essentially to allocate limited resources while optimizing some objectives and achieving a final goal. And that's why it's so important in both our lives and in industry. So now I'm going to introduce a type of scheduling problem I'm investigating. So we're given a set of machines that are identical and parallel, which means they can process different jobs at the same time. And now we're to schedule a set of n independent jobs onto these machines. And a job only needs to be carried out on one of the machines, and a machine can only process one job at a time. So each of these jobs has a fixed processing time. And we also consider a sequence-dependent setup time characteristic. So which means after each job is completed, the machine needs to take additional time to prepare for and transition to the next job. And the setup time is dependent on the order of the two jobs, as shown in my example. So finally, there can be no interruptions during the processing time or the setup time. So we're to work out a schedule of the jobs on these machines with the objective to minimize the make span. So this Gantt chart is an example of the job schedule with processing time and the setup times. So we also pay attention to the completion time on each machine, and the latest completion time, Cmax, is referred to as the make span. So in this instance, the make span is 14 minutes, and this happens to be the optimal solution for this problem. So now we're fully familiar with the problem, let's talk about what we do. So you remember in the title, I mentioned a single resource model, and you may wonder what that is. So essentially, each machine is considered a resource, and the problem setup I just showed you treats each machine as an alternative resource. With some transformation, our model considers all machines as one single resource, and we'll go into deeper details later. So this single resource model is inspired by previous work on EVRP, which stands for electric vehicle routing problems, and it's mathematically similar to the scheduling problem. So the author proposed a single resource transformation, and it demonstrates better performance than the traditional alternative resource approach. And this type of scheduling is NP hard, which means it's a hard computational problem and cannot be solved in polynomial time. Therefore, there is ongoing research proposing new optimization methods to tackle it. So our model already shows advantages in EVRP, and our work modifies this model to use it for scheduling and provides a new way of tackling this difficult problem. We hypothesize it to demonstrate similar advantages as in EVRP, and this includes a higher runtime efficiency and reduced memory usage. We also hope to understand and learn how the single resource model works in different settings and identify its other areas of usage. So both the models use constraint programming that consists of a wide range of techniques from artificial intelligence and operations research. It's a generic tool often used to solve combinatorial optimization problems, and it enforces conditions or constraints on solutions, and the values of the decision variables must satisfy all constraints. And it usually has an objective function that indicates whether the solution is trying to minimize or maximize something. But the goal could also be to find one feasible solution that does not violate the constraints, like in Sudoku. So we compare our single resource model to the traditional alternative resource model, where each machine is considered as an alternative resource. So we use these three decision variables as listed, and this diagram here shows the two machines as sequence variables, and each job or each bar is an interval variable. So for each job, we created m numbers of optional interval variables on each machine, And the alternative constraint makes sure that each job is only present in one of the optional activities across the machines. So we also use a no overlap constraint on the sequence variable to ensure the interval variables and the setup times in the sequence do not interfere temporally. And the single resource model only utilizes one machine as a single resource to schedule and does not explicitly represent each machine. It schedules the activities over an augmented horizon. So in this diagram, each individual horizon segment has a length of h, and we have m numbers of horizon segments that represents different machines in real life. So essentially, we schedule it like only one machine is going through all the jobs, but each time it enters a new horizon segment, it acts like a new machine. We also include these dummy jobs at the end of with processing time 1 and setup time 0 at the end of the horizons to prevent
20 to 30 minutes. I'll be there.
Sorry, is someone speaking?
Where? Okay, you'll let me know where in the Irvington Park you guys will be.
Sorry, is someone speaking?
So will you still be there in 20 minutes?
No, just keep going.
Okay. Okay, so we have dummy jobs at the end of each horizon to prevent a job from overflowing into the next horizon. And we still use an interval variable and a sequence variables, but this model does not, and we have an no overlap constraint as well, but this model does not require the optional interval variables, and it also has less complicated constraints. So we predict that these characteristics would help reduce the memory needed and to store the model and improve the runtime efficiency. So our next step is to implement both models in software. And we start with the high-level CP solver called MiniZync on the left. But soon we realized that it does not have all scheduling features we desired. It lacks control over low-level details. So we moved on to use the state-of-art solver called CP Optimizer. So we generated benchmark instances with random values, but we controlled the number of machines to be between 2 and 5. And each m value, we consider these 3 job numbers. So in total, we have 12 mn combinations, and we create 10 instances for each combination. We also enforce a 5-minute time limit for each instance. All these number decisions are based on previous literature and some preliminary testings. So we ran experiments with each model, solving the benchmark instances. Going back to our hypothesis, we decided to record the memory usage as well as the final solution it finds at the end of the time limit. So the results are shown in this graph, with blue as the alternative resource model and gray as the single, or black as a single resource model. So the bar graph with axis on the left shows the number of instances out of 10 where a model is able to find the best known solution, BKS, between the two. And the line graph with axis on the right records the average memory usage for each model. We observed that as the problem size gets bigger, AR, which is alternative resource model, requires more memory, whereas SR's memory usage stays pretty much the same. We also see that SR is able to find a better solution or the best known solution more often than AR within the time limit. So therefore, we conclude that the single resource model demonstrates advantages in parallel machine scheduling over the alternative resource model, as it finds a better solution with less memory usage. As we explore the modified model from a different problem and put it in use for scheduling, we find that it has both higher time and space efficiency, and it can serve as a new way to help reduce the computational costs in tackling such a complex scheduling problem. With some analysis on our results and previous literature, we also suggest that the advantages of the single resource transformation will be more prominent in problems with similar setups as the EVRP. So as such, we propose the investigation of other routing problems where surgical scheduling in healthcare can be beneficial and useful for future work. All right, thank you.
So thank you, Cathlyn, for your presentation. So once again, I'd like to address the judges and ask you to please unmute and ask if you have any questions.
Sure, perhaps I can start. It's Professor Busman. Cathlyn, that was a really a lovely presentation, and it's
Thank you.
as the chair of MIE, I might say it's nice to see something that one of my colleagues is doing, like Professor Beck. So good on you. So I have a not that I understand this stuff particularly well, but maybe a question. So the simulations that you ran, the results that you ran were with a few machines, 2, 3, 4, 5 machines, and you know 20 instances or 50 instances, number of jobs. So so can you speak briefly about so that maybe I'm wrong, but that strikes me as a toy problem, right? Which is perfectly fine. It's we're just you're testing out an algorithm, but can you comment on how well you think this would scale to lots of machines and thousands of jobs?
Right. So we actually did some testing with a lot larger problem instances. So we had 10 machines, 20 machines with like 100 jobs. We even had 100 machines with 1,000 jobs. So we found similar patterns in those large problem instances. And we also found that for those larger problem instances, if we enforce a 5-minute, if we enforce a 5-minute time limit, and if we enforce a 10-minute time limit, they actually find the same results. So the solver just is not able to find any better solutions between like 5 minutes and 10 minutes. So so with testing on those larger problem instances, we can kind of see that this demonstrates the overall trend of the comparison between the two models.
Thank you.
Can I just ask two quick questions, Cathlyn? The jobs can be done in any order, or is there an ordering between the jobs?
That's a decision for the algorithm to make. So it has to take in consideration with the sequence dependent setup time. So essentially it can be in any order, but it's trying to put it in the order where the make span is minimized.
Okay, and just one more quick question on the traditional way of doing it. When you showed make span, you were sort of taking the maximum length of basically 2 horizontal sort of Gantt charts, right?
Right.
In the traditional way of doing it, but in this sort of single resource way of doing it, is it actually solving the same problem? It seemed to me there you're actually summing up the sum of horizon times, or do you also force H to be the longest one? Right.
So H is a fixed number, so it's usually given with a problem. And the completion time on the single resource should be at the end of the job on each horizon segment. So for this one, it would be here, and then this one will be here. And then it's taken from the previous H and the end time, like this would be the make span.
Yeah, okay, got it, thanks.
Sorry, that wasn't clear. I should have put an indication on that. Thanks for the question.